solving separable differential equations. Last class we learned about how to verify the solution of a differential equation. And some differential equations are actually very difficult to solve, to find the solution. But there is one type which are called separable differential equations that are relatively easy to solve. And this is actually the only type you're going to learn about in this class. So before I begin this, solving separable differential equations, I want to quickly remind you of some algebra stuff. One of them is this: if you have A over B equals C over D, you know you can cross multiply. So this is equivalent to multiplying the A and D. So like this, AD equals multiplying the B and C, BC. So it's called cross multiplication. And you can also go from this side to this side. So for example, if you have AD equal BC, you can see that if I divide both sides by A, then this cancels this. I get D equals BC over A. So it's as if I have AD equal BC. I can just get rid of A over here, and then the A appears at the bottom here. Or if I have, for example, AD equals BC, I want to get rid of C on this side. I have to divide by C. So it's as if C disappears from here and then reappears at the bottom here. So AD over C is equal B. So these are all equivalent. I wanted to remind you this because I'm going to use that while I am solving these problems. And the other thing I want to remind you of is ln and the properties of ln. So you know that generally when we say log A base B is C, that is equivalent to B to the power of C is A. And ln of, for example, x is log x base E, the special number E, the Euler's constant. So for example, if you have, let's say, ln of x is equal, let's say, C, that's the same as having log x base E is equal C. So if you want to isolate your x, you would write x is equal E to the power of C. Yes. So the way I memorize this is I think of these arrows, and then I say to myself that this means B to the power of C is A. So that's the meaning of these arrows for me. And we also had these properties that you may need to use for solving these problems. If you have ln of x plus ln of y, that's the same as ln of xy. If you have ln of x minus ln of y, that equals ln of x over y. And if you have ln of, let's say, x to the power of r, this r can be moved to the front. So that's r ln of x. So these three properties also, they're properties of logs. They are true for the log of any base. So they're also true for log of base E, which is ln. So just want to quickly remind you of these properties so that when I use them solving these problems, you know what I'm referring to. Okay. So example 1, find the general solution of the first order differential equation. And the differential equation given is y prime is xy over x squared plus 1. So what does this mean? Find the general solution. So we saw last class that the solution to a differential equation is a function or a family of functions. And if you have the family of functions, that family of the functions is called the general solution to the differential equation. So in order to find the general solution to this, in other words, I'm looking for the function y equals f of x, or a family of functions that will satisfy this equation. This is what I have to do. I replace y prime with the Leibniz notation dy over dx is equal xy is over x squared plus 1. So that's the first step. Then, as you can see, I have a fraction over a fraction. So I can just use dy and dx as if they are numbers or they are variables, and I can cross multiply. So if I cross multiply this times this times this, what do I get? I get xy dx is equal x squared plus 1 is equal dy. My next step would be to get all the x's on one side and all the y's on the other side. So I want to separate the x's from the y's. This is not always possible, but it is possible in the case of separable differential equations. So that's the name, that's where the name comes from, separable. These are separable because you can put all the x's on one side and all the y's on the other side. So this should go to this side, and this y here should go to this side. So I can just, this y here can disappear from this side and then appear here at the bottom, and this can disappear from this side and appear here at the bottom. I'm simply dividing both sides by y and then dividing both sides by x squared plus 1. So if I rearrange this, I can write that as x over x squared plus 1 dx equal 1 over y dy, or dy over y. Is this clear what I'm doing?
Yes, sir, but I have a question.
Go ahead.
How do you know if it's separable? Like in an exam?
You don't know. You don't know.
Like,
for a general differential equation, you don't know whether it's separable or not. But if you're worried about your test and your exams, this is the only type of differential equation we're going to learn about. So the problems that you will deal with, all of them are separable.
I don't understand. What do you mean?
You're not going to be given any differential equation that is not separable. Yes.
Oh,
so
okay.
the problems that you're going to deal with in web work or in the book or the test, final exam, all of them are separable differential equations. Yeah, but in general, you don't know. In general, this could be the first thing that you try, but sometimes they're not separable. Did I answer your question?
Yeah, I understand. Thank you.
Okay. So what is the next step? You're going to take the antiderivative of both sides. You can find the antiderivative of this side and the antiderivative of that side, and this will help you find the answer. Salma, you have a question?
Yes. Why do the y and the x squared plus 1 cancel at the same time?
They don't cancel. It's like if we have AD equals BC, yes, this would be equivalent to having AB is equal CD. Yeah, because A times D is equal B times C. It's same story. So think I want Y to be on the other side. I'm going to redo that. So I began with Y prime is equal XY over X squared plus 1. I wrote Y prime using Leibniz notation as dy over dx is xy over x squared plus 1. Then I cross multiplied. I got x squared plus 1 times dy. So this times this is equal this times this, xy over dx. Okay. Now my goal is to have all the x's on one side and all the y's on the other side. Okay. So I have the dy here. I'm going to move all the y's here. I have the dx here. I'm going to move all the x's here. So this I should get rid of this part and bring it to the right. And I should also get rid of this y and bring it to the left. Now, how do I do that? I can divide both sides by x squared plus 1. If I divide both sides by x squared plus 1, I'll be here. dy, so on this side, this cancels this. I get dy is equal x, y, dx over x squared plus 1. And now I want to get rid of this y here, so I have to multiply both sides by 1 over y. Then this cancels this. I get x dx over x squared plus 1 is 1 over y dy. I separated the x's from y's. Make sense?
Yes, thank you.
Sure. What I'm trying to tell you is that since if you have AB equals CD, you can easily move things around if you just have this concept in mind. If you want A on the other side, you can divide by A on both sides. So it's as if A disappears on this side, appears at the bottom here. So I'm just using the same concept. When I look at something like this, x squared plus 1 dy is equal xy dx. I say, okay, I want y on the other side, so it will be at the bottom. So I get dy over y is equal, and I already have x dx on top here, and then this needs to go on the other side. It will appear at the bottom. Make sense? And then you're going to take the antiderivative on both sides. So let's do that. Yeah, actually, I don't need to copy that. It's over here. I have it over here. So dy over y is equal antiderivative of x squared plus 1 dx. So when you take the antiderivative for this one, it's clear it's ln of absolute value of y. For this other one, you need to do a substitution. You take the derivative x squared plus 1 to be u. Then the du is going to be 2x dx. You can multiply by 2 here, divide by 2 outside. And then again, it will become du over u. So it's going to be 1 over 2 ln of absolute value of x squared plus 1. And then here you can have a plus c1. On the other side, you can have a plus c2. Because normally you have a plus c, but since c1 and c2 are independent arbitrary numbers, so for the left, I'm going to use c1, and for the right, I'm going to use c2. Are we good? Now, if I move c1 to the other side, I get ln of absolute value of y is equal 1 over 2 ln of x squared plus 1 plus c2 minus c1. Now, this c2 minus c1 is also an arbitrary number. If c1 is an arbitrary number, c2 is also an arbitrary number, any constant. So the difference would also be an arbitrary number. So I can just call this c. And from now on, I'm going to put just plus c on one side. So if I have something like this, antiderivative of, let's say, f prime of x dx is equal antiderivative of g prime of x dx, that would be f of x is equal g of x plus c. I would just put c on one side, not on both sides, just because of this logic here. If I have c1 on one side and c2 on the other side, I can move c1 to the other side. I get c2 minus c1, then I can call that c. And this can be done for every problem like this. So after this point here, the only thing you need to do is to isolate your y. Sometimes you will be able to isolate the y, and sometimes you will not be able to isolate the y. So here we have some logic about C1 and C2, where C1 and C2 are arbitrary constants of integration. If we choose C such as C1, C2 minus C1 is ln of C, I can use those properties of ln that I was talking about. So I can also call this ln of C. It really doesn't matter because it's an arbitrary number. So I get ln of absolute value of y is equal 1 over 2 ln of x squared plus 1. I also got rid of the absolute value signs because x squared plus 1 is basically positive. I don't need absolute value. Plus ln of c. So ln of y is, so if I use the third property, you can see that this 1 over 2 can be moved here to the position of power. So it becomes ln of x squared plus 1 to the power of 1 over 2. That was the third property I mentioned, plus ln of absolute value of c. And then another property of ln is that a summation can be written as a multiplication. So ln of x plus ln of y is ln of x times y. So this becomes ln of absolute value of y is equal ln of this times this. So absolute value of c times root x squared plus 1. So if ln of y, ln of absolute value of y is equal ln of c root x squared plus 1, then that means y is equal c plus absolute root of x squared plus 1. Yes, I just have ln on this side. I also have ln on the other side. If ln of absolute value of y is equal ln of absolute value of c plus root x squared plus 1, that means this has to be equal this. So I get absolute value of y is equal absolute value of c times root x squared plus 1. Now, yeah. So I just removed the ln's. Since c here is an arbitrary constant, it could be positive or it could be negative. In general, if I have absolute value of a is equal absolute value of b, that would mean a is either plus or minus b. So this could mean that y is either plus or minus c root x squared plus 1. However, since c is an arbitrary number, it could be positive, it could be negative. It really doesn't matter to put that plus or minus. So I can say y, my solution is x squared plus c times x squared plus 1. That is, any function that has this form would be a solution to this differential equation. For example, a particular solution, if I pick c to be 10, y equals 10 root x squared plus 1, or minus 10, y equals minus 10 root x squared plus 1. These y values, these y functions, they will all satisfy this differential equation, as long as it has the form c times the square root of x squared plus 1. Any questions?
Yes, sir. Can you repeat why there's 10 and then minus 10?
Because c is an arbitrary number. I can put any number for c. Yes,
Okay.
I was just giving examples of particular solutions. Yes, the general solution is what we are trying to figure out. So you would stop here. That's the general solution.
So after you can put any number.
If you're asked to give a particular solution, yes, you can put any number for C and get the answer.
Oh, okay.
But in most scenarios, in most cases, you're asked for the general solution, so you have to stop here. Sometimes you're supposed to give a particular solution, but for those problems, you're given an initial condition. And we will see some problems like that later on.
So generally, I will just put a C.
Yes.
Okay, thank you.
If you're asked for the general solution, you just put a C over here, and then you stop. That's your general solution. And what is C? C is any number that you like, arbitrary number. Okay, so do we all understand how this 1/2 became the power? I'm just using these properties. I want to express them very quickly again. If you have r times ln of x, this is ln of x to the power of r. So here I had 1/2 times ln of x squared plus 1. So this became ln of x squared plus 1 to the power of 1/2, which is the same as ln of root x squared plus 1. Or if I have ln of x plus ln of y, this is simply ln of xy. So in this case, we had ln of a, or ln of a plus ln of b, then it became the product of these two. If you have ln of root x squared plus 1 plus ln of absolute value of c, yes, you can multiply these two, write that as ln of the product of these two. And then it doesn't matter whether you put the absolute value sign around all of this, because this is always positive. Root x squared plus 1 is always positive. So this is the same thing as having ln of absolute value of c root x squared plus 1. So that's why you have this over here. And again, if you have ln of a equals ln of b, that simply means that a is equal b. So get rid of those ln's. This is what we did here. We had ln of absolute value of y is equal ln of absolute value of this expression here. So ln's are gone. You get y equals c root x squared plus 1. In general, if you have absolute value of a is equal absolute value of b, this does not imply that a equals b. A could also be minus b. So for example, absolute value of 2 and absolute value of minus 2 are the same, right? Both of them are 2. So this is true, but it doesn't imply that 2 is equal minus 2. So in general, absolute value of a is equal absolute value of b. That means a is equal either plus or minus b. It could be either of the two situations. They could be the same, a and b could be the same, or one could be the negative of the other one. In this case, we don't need that plus and minus before the c, because c is an arbitrary number. So if c is an arbitrary number, then plus minus c is also an arbitrary number. So you might as well just write c. Let's do another one. And hopefully by doing these examples, you'll get the hang of it. I have y e to the power of x plus y squared minus y times y prime is equal 0. I'm going to first isolate my y prime. So if I isolate my y prime, I have y squared minus 1 times y prime is equal minus y e to x. That means y prime is equal minus y e to x over y squared minus 1. And I can now replace y prime using Leibniz notation with dy over dx. And I can do the cross multiplication now. So minus y e to x dx is equal y squared minus 1 dy. Everything's good so far? I isolated my y prime, and then I replaced y prime with dy over dx, and then I cross multiplied. Now I want to separate the x's from the y's, so I can see that the only thing I need to do at this point is to get rid of the y on this side, yes, or the minus y, doesn't matter. I'm going to get rid of just the y, and it will just go from this side, it will appear at the bottom here. So I get negative e to x dx is going to be y squared minus 1 over y dy. So this turned out to be a separable differential equation, because the x's and the y's, I could separate them. And now you have no y on this side and you have no x on the other side. Next, I'm going to take the antiderivative on both sides. I get minus e to the power of x plus c on this side. And on the other side, you can see I can write this as y minus 1 over y. So the antiderivative of this with respect to y is going to be 1 over 2y squared minus ln of absolute value of y. I don't need to write plus c on both sides. Yes, I can just see plus, I can write plus c either on this side or on the other side. It doesn't matter. So that would be the general solution. I don't think I can isolate y in this case, and that's okay. So in this problem, I can just leave this as it is. This is the general solution in implicit form. Whenever y is isolated, like we were able to isolate y in the previous problem here, this is called the explicit form. Simply means y is isolated. And if you cannot isolate the y, you can just leave the general solution like this, and that would be the implicit form. Are we good?
Question.
Yep.
Could you have sent the negative sign to like the y when you
The
switched
negative, then yeah, I could also do that. So it doesn't matter if I just multiply both sides of this equation. If I multiply both sides by -1, I would get that situation.
Okay.
So that's okay. Now, this is an initial value problem. I have the general solution, but it is asking me for a particular solution which also satisfies this initial condition. Yes, it says find the particular solution of the differential equation, this differential equation that I just solved, that also satisfies this initial condition. So I can just plug in, you know that this is like having f of x is equal 1. Or this is the same thing as saying that this function passes through the point 0, 1. So I can plug in 0 for x, I can plug in 1 for y, and figure out what c is in this equation here. Yes, because again, that general, that condition, y0 is equal 1, this is the same thing as saying that this curve passes through the point 0, 1. So I can plug in 0 for x, I can plug in 1 for y, and get c, my unknown. Yes, Salma, you have a question?
Yes, how do we know if y is or is not solvable?
You try that. If you can isolate y, then much better. You have the form, you have the explicit form. But if you cannot isolate it, then it's implicit. Yeah, so how do you know? By trying it.
Okay, so if it's
Yeah,
impossible,
there is no way you can tell by looking at the differential equation that eventually y is going to be would it be possible to isolate y or not? You can't tell. Yeah?
so
So you have to solve it, and then at this point you see, okay, I have x squared, I have y squared, and I have ln of absolute value of y. Is there a way I can factor out the y, solve for y? No. So I just leave it like that. And also for this problem here, it is not asking us for the general solution. So the focus is for the particular solution. So I can just figure out what C is and then see whether I can isolate Y.
Sir, I have a question.
Yes?
Why isn't there a C on the other side, like on the 1/2 times y squared minus ln of absolute value of y?
I explained that in the previous problem. You can have a C1 here and you can have a C2 on the other side. But when you move the two C's to one side, you either get C1 minus C2 or C2 minus C1, right?
Mm-hmm.
You can call that C then.
Okay.
Because, as I said, these are arbitrary numbers. C1 is arbitrary number, C2 is an arbitrary number. So C1 minus C2 or C2 minus C1 or 3 times C1.
We just have to put C on either side.
Yeah, all of them could just be replaced with C. Yes.
Okay.
So if C is an arbitrary number, then I can replace 3C with C. I can replace minus C with C. I can replace C over 5 with C. I can replace C1 minus C2 with C, as long as these are just arbitrary numbers. Okay, so let's just, in this equation that we found, 1/2 y squared minus ln of absolute value of y equals negative e to x plus c. So that's the one over here that we found, 1/2 y to 2 ln of absolute value of y minus e to x plus c. Okay, so in this, we're gonna plug in the point 1, 0, 1 to find what c is. Let's just plug in 1 for y. We get 1/2 1 squared minus ln of absolute value of 1 is equal negative e to the power of 0 plus c. You can see on this side, ln of 1 is 0, because generally log whatever base of 1 is going to be 0. Yes, because b to the power of 0 is 1. And e to the power of 0 is also 1. So on this side, we get negative 1 plus c. On the other side, we get 1/2. So that means c is going to be 3/2. So I can say that the function has the form 1/2 y squared minus ln of absolute value of y is equal minus e to the power of x plus 3/2. So if you give me this answer, that's absolutely fine and it's correct. It looks a little bit different from what we have here. I'm going to show you how it's different and why it's different, but basically this answer is also correct. What has been done here is simply multiplying both sides by 2 to get rid of the 1/2. You can do that. You can multiply both sides of this by 2. When you have an equation, you can multiply both sides by any non-zero number. And if you do that, you're going to get y squared minus 2 ln of absolute value of y is equal minus 2e to x plus 3. And this here is the same as y to the power of ln of y squared, just because, as I told you before, r ln of x is equal ln of x to the power of r. So this can be moved to the power position here. So if I just do this, move this to the position of power, I get root absolute value of y squared, which is the same thing as y squared because it's positive. So I get y squared minus ln of y squared is equal minus 2 e to the power of x plus 3, which is the same thing as you have over here in the book. But again, if you leave it like this, that's also fine. Are we good? Any questions? So that was an example of an initial value problem. That is, you have a differential equation. You would be able to separate the variables and get the general solution. and in your general solution there will be some c. Since you have 1 point from the curve, you can plug in the values for x and y and figure out what c should be. That makes it an initial value problem. Okay, let's do one more example. Example 3. It says find an equation describing f given that you have these two conditions. One, the slope of the tangent line to the graph of f at any point p, x, and y is given by this expression, minus x over 2y. But we know what the slope of the tangent line is. The slope of the tangent line is basically the derivative. So when it says the slope of the tangent line to the curve at any given point of the curve is given by this expression, negative x over 2y, basically this is the derivative, y prime. So this is our differential equation. Now the second condition is the initial condition. It says it should pass through the point 1, 2. That means the point 1, 2 must satisfy the equation of the curve. Okay. So it's just like the previous problem, just a little worded differently. You're given a differential equation and one initial condition. So from the differential equation, using the separable, by separating the x and y, you're gonna get the general solution, and then plug in 1 for x, 2 for y, and figure out what c is. Let's do that. We have minus x over 2y is equal dy over dx. That means minus x dx is equal 2y dy. X and y are already separated. Let's just take the antiderivative with respect, antiderivative on both sides. We get negative 1 over 2x squared is equal y squared plus c. If I multiply both sides of this by 2, I'm going to get, by negative 2, I'm going to get x squared is equal negative 2y squared plus c. And the reason that I don't multiply the c by 2 is that if I multiply c by 2, I get 2c, but 2c is also going to be an arbitrary number. Yes? So I can replace 2c with c because it's an arbitrary number. So it becomes x squared plus 2y squared is equal c. So that would be the general solution. Or I can leave it like this, or I can leave it like this, doesn't matter. All of these are good as the general solution. We're looking for the particular solution, so let's just plug in 1 for x and 2 for y to get c. So 1 squared plus 2 times 2 squared, that's going to be c. That's 1 plus 8, that's 9. Okay, so the particular solution which satisfies both conditions is going to be x squared plus 2y squared is equal 9. X squared plus 2y squared is equal 9. Yes, questions? Okay, then. So from this set, you're supposed to do which problems? Let's see. 9.2, 1 to 11, 13 to 24, and then 26 and 27. I'm going to do one of them for you. Let's do the last one. So it says 1 to 11, these problems here, and then 13 to 24, 13 to 24. These are initial value problems. For these ones, you just find the general solution. For these ones, you find the general solution and then the particular solution using the initial value. And 27 is also the same story. I'm going to do the last one for you. We have 3x squared e to the power of minus y. That is our y prime. And we have y0 is equal 1. Okay, so that means dy over dx is equal 3x squared e to the power of minus y. I can write this as 3x squared over e to the power of y, just moving e to negative y to the bottom, and then it becomes e to y. I can now cross multiply. This times this is equal this times this. Antiderivative on both sides. I get e to y is equal x to the power of 3 plus c. I don't need to put c on both sides. I just put c on this side. So for this problem, I can easily isolate y because I can take ln on both sides. If I take ln on this side, and if I take ln on the other side, this is going to be, if I have ln of e to the power of y, that's y ln of e, but ln of e is 1, so that's why. Y is ln of x to 3 plus c. So for this particular problem, it was easy to isolate y. Now, let's get c. If I plug in 0 for x, 1 should be, y should be 1. I can plug in 0 for x and 1 for y and get the answer for c. So 1 is equal ln of 0 cubed plus c. So that's ln of c. Okay, what should c be so that ln of c is 1?
Zero?
Nope. Ln, we just saw it here.
E.
E, that's right. Ln of e is 1. Yes, so don't forget, generally when you have log b base b, that's going to be 1 because b to the power of 1 is b. So for ln, which is the same thing as log e, it's ln of e that is 1 because ln of e is like having log e base e. So that means c is e. So y is ln of x to the power of 3 plus the special number e and e. And that's it. That's the particular solution. So here you have the general solution where c is any arbitrary number. This part general solution will satisfy the differential equation. And if c is equal to the special number e, then it will also satisfy this initial condition, y of 0 is equal to 1.